In this video, we are going to continue our study of the Einsteinian equivalence principle and its consequences. One of the main results of the previous video was that the Einsteinian equivalence principle implied, or almost implied, that gravity should be represented by a metric. You can think of the principle of general covariance that we are going to enunciate now as an adaptation of the Einsteinian equivalence principle to theories of gravity in which gravity is represented by a metric. So these are called metric theories of gravity. And the formulation of this principle is as follows. This principle can be formulated as follows. A law of physics agrees with the Einsteinian equivalence principle if these two conditions are met. First of all, in absence of gravity, and this means in the context of metric theories of gravity that the metric is the Minkowski metric, but also that this affine connection is zero, because remember that this affine connection can be different from zero if the metric is the Minkowski metric but expressed in certain coordinates which are not does not correspond to an inertial reference frame. So there are inertial forces, and then gamma is different from zero. So in absence of gravity, which means these two things, it reduces to a special relativistic law of physics. And the second condition is that it is form invariant under general coordinate transformations that we abbreviate as GCTs. Okay, sometimes this general covariance, which is alludes really to this condition too, is understood as only this second condition. But you have to be aware that classical physics, or the laws of classical physics, can also be formulated in a general covariant form. So in such a way that they are form invariant under general coordinate transformations. For instance, Newtonian gravity can be formulated in a completely coordinate invariant form, and this is the so-called Newton-Cartan formulation. Or Newton-Cartan theory of gravity. But this Newton-Cartan theory, when you adapt the coordinates to a universal time and to a particular inertial set of coordinates, then it is completely equivalent to the Newton theory. This formulation is, however, very interesting because it allows you to generalize it. A second observation is that the condition I, a first condition, is what basically contains the Einsteinian equivalence principle. Remember that it says that when you are in a freely falling frame, which is possible in the neighborhood of any event in space-time, the laws of physics take their special relativistic form. This is telling you that when you are in one of these free falling frames and the metric is at least locally Minkowski and this gamma is at least locally zero, then you have this special relativistic form. So this is the condition that the laws of physics have to satisfy. And this second condition is a technical condition which, as I said, can be satisfied also by other theories which are not even special relativistic. They are purely classical Newtonian or Galilean. The difference is that this second condition is just optional in the context of classical physics, so I can write the Newton equations in a coordinate invariant form or not. I can write it in standard inertial frame coordinates and using the universal time. But in the case of gravity, I cannot do it. I have to use a general covariant form for my equations. The result of this principle of general covariance is that it gives us a prescription which is called minimal coupling, and which we will study. To start with special relativistic theory and generate from it a theory which satisfies this principle of general covariance. Okay, this minimal coupling recipe obviously contains the replacement of the Minkowski metric, which is necessary for special relativistic theory, by a general metric, but this is not enough. There is more. Okay, more that I cannot describe at this point because we need more mathematics in order to understand why we need these additional tools. Now let's go back to the experimental consequences or the experimental predictions of the Einsteinian equivalence principle. Einstein himself realized in 1907, when he first formulated the principle of equivalence, that there were some experimental consequences of his principle, even though he was still far from the final formulation of a theory of gravity satisfying that principle. But just following the principle itself, you could arrive to certain conclusions, like the bending of light rays. He could not quantify how much light would be bended by the sun, for instance, without a theory, but he could really say that this effect would take place. There are two more effects, okay, or if you want, is one, which is the gravitational time dilation, and the redshift, the gravitational redshift is really a derived effect that can be deduced from the equivalence principle. But in this case, they can be quantified, which is very interesting. The way in which Einstein himself did this was via a thought experiment again. So he considered a box of height h. Okay, here height will be measured in this direction. Okay, and this box is assumed to be moving with constant acceleration g. Okay, this happens in the reference frame in which we as observers are sitting. Okay, and of course this box is just a way of describing an accelerating frame. Okay. Then in this setup, the bottom of the box, so this line here, and the top of the box represent points which have the same acceleration but which are separated by a distance h in the direction of the acceleration. Furthermore, we are going to assume that at time equals 0, the box or the bottom of the box is at x equals 0. So let's describe the situation at t equals 0. We have the box with the bottom at x equals 0. Okay, this would be h. And then this would be h. Then at this instant, t equals 0, we send a pulse of light from the bottom of the box, x equals 0, towards the top. If this pulse of light takes a time t1 to reach the top of the box, you realize that the box of the top of the box has suffered a displacement from h to h plus a half g t1 squared. We are describing this in our coordinate system, which is an inertial coordinate system with coordinates x and t. Okay, so this would be this point, and this is where light would arrive. But because our coordinate system is inertial, and then in it, by definition, the metric will be Minkowskian, and the speed of light will be c, then if this is the distance that light has traveled in this time t1, okay, this is also equal to the speed of light times t1. Okay, then an elementary operation helps you to find that t1, which satisfies this second order equation, is equal to c over g times 1 minus the square root of 1 minus 2gh over c squared. Okay, now let's assume that a small interval of time later than t equals 0, we send another pulse of light. Okay, so this pulse of light starts at delta t, and at delta t the situation is more or less like this, as seen from our reference frame. Okay, the box has moved g 1/2 of g delta t squared. So this is where the bottom is. The bottom of the box is now, and the top of the box is at h plus 1/2 g delta t squared. Okay, light starts from the bottom and it reaches the top at a time t2 in the reference frame t. So this is not an increment of time, but the absolute time at which it reaches the top. So this will be, let's exaggerate this just to simplify where we write the formula. Okay, this doesn't have to be a good scale representation. So it will arrive here. Okay, so now we would like to make an argument similar to the one we did here for the first pulse of light, but now this pulse of light has been emitted from the bottom of a box which is moving with a certain speed already from this reference frame. Okay, I didn't say but explicitly, but it was implicit that at t equals 0 the speed of the box b was 0. Okay, otherwise this would not be true. Now you have to take into account in this calculation that there is some initial speed, okay, which will be g delta t, and in order to describe to make this calculation and this reasoning that light moves at a constant speed in an inertial frame, you have to think of a different inertial frame than the original one. Okay, a frame which is moving, okay, at the moment delta t at a speed g delta t, and you have to make a Lorentz transformation to that reference frame, because instantaneously it will be this box will be at rest at that time. However, if you make this calculation explicitly, you will realize that the Lorentz transformation that you have to make, okay, contains terms of velocity multiplied by time. Then since the velocity already has this delta t, you will get corrections of order delta t squared that we can ignore. So we can still work to this order of approximation, to first order in delta t, in the original coordinate system inertial reference frame that we are using. Okay, so now we have that the final position of the light ray is h plus a half g t2 squared minus the original position is half of g delta t squared, but to the order in which we are working, we just ignore this term. This is equal to the speed of light times the time that the light pulse has been moving. So this will be the final time minus the initial time. This is first order in delta. Okay, so an analogous calculation to keeping always terms to first order in delta will give us the following result. Okay, that T2 is equal to T1 plus delta T divided by square root of 1 minus 2gh divided by c squared. Okay, let me do this calculation explicitly now, just for your benefit. So I take this equation and I write the polynomial in the standard order. So starting with the term of highest degree, T2 is the unknown, then there is minus c T2 h and plus c delta t, and this is the independent term. So now apply the standard formula. Okay, instead of equal to 0, this should be really approximately 0. So if we want to be really rigorous, we should say this is approximately. Okay, and then it is minus b, which is c, plus minus b squared, which is c squared, minus 4 times a, so this is 2g, and the last term plus c delta t, and everything divided by g. Okay, the first observation is that the solution that we want to keep is this one. This is the one which is physically relevant. Just think a bit about it, and you realize that this has to be always smaller than c divided by g. And okay, we want now to expand this in powers of delta t and stay at first order. So first we operate on the parentheses, and we get c minus the square root of c squared minus 2gh minus 2gc delta t, and everything divided by g. Now this is the delta t independent term, so we want to take it out of the square root. So we get c minus c squared minus 2gh to the power 1/2, and we are left with 1 minus 2gc delta t divided by c squared minus 2gh, and everything divided by g. I mean, the goal of writing this in this way as a square root of 1 plus something delta t is because then approximately we have, this is 1 minus a half of that something delta t. So we can expand this. So first we write the factor, and the expansion is 1 minus a half of what we have there, 2gc delta t divided by c squared minus 2gh. The factors of 2 cancel, and now we again operate on the parentheses. So this is c over g minus c squared minus 2gh to the power 1/2 divided by g plus, and this well, partially cancel, the factors of g cancel, so you have c delta t divided by c squared minus 2gh to the power 1/2. And now we're almost there. If we, so this is equal, and we take a common factor, g over c over g, 1 minus, and if I take a c out, what I get is 1 minus 2gh divided by c squared to the power 1/2. Okay, so these are the first two terms, plus, and let me divide both numerator and denominator by c, and we get delta t divided by 1 minus 2gh divided by c squared to the power 1/2. Now, we should recognize this as the time t1 of arrival of the first light pulse, like we found here. Oops, here, okay, in this box. So we write t1, and since this is t2 approximately, we have that t2 minus t1, the difference in times of arrival to the top of the box, that we can call delta t, is related to the difference in the times of departure of the light rays, delta t, by this factor 1 minus 2gh divided by c squared to the power 1/2. This is a factor that should be smaller than 1, which means that this will be delta t divided by it will be larger than delta t. So, sorry, capital delta t will be larger than the small delta t. And this is the fundamental formula. Okay, now if we want to interpret physically this factor, we can remember that according to the principle of equivalence, a constant acceleration is equivalent to a homogeneous gravitational field with a potential phi equal to the acceleration g times x, the direction which it propagates. This means that we can rewrite this same formula, delta t, in this way: 1 plus the potential at the top, the gravitational potential at the top, minus the gravitational potential at the bottom, divided by c squared. Okay, delta t. Let's check that this equation coincides with this one. So phi at the top, the potential energy at the top, is it's just the gravitational potential at the top. It's not an energy here. It's just gh, and at the bottom is 0. Okay, this will be plus an arbitrary constant if we want. Okay, but we have decided this origin of potentials, but it doesn't matter because it is only the difference that matters in this equation. And okay, this is as it should, because physical effects should not depend on these constants. Now you get 1 plus gh divided by c squared, and if you expand 1 minus 2gh divided by c squared to the power minus 1/2, okay, for small values of gh over c squared, this is 1 plus gh divided by c squared. So this happens if gh is much smaller than c squared. Now this condition should be familiar to you. If we were talking about potential energies of a particle, okay, we can multiply this inequality by the mass of some particle, which is not there, but still, this is telling you that the potential energy of the particle, gravitational potential energy of the particle, is much smaller than the energy of the particle at rest. And this is the condition that we used at some point to prove that the non-relativistic limit of particle moving in the background of a metric whose non-trivial component was 1 plus 2v divided by mc squared was that of a particle moving in a potential v. Okay, so and the condition was here that the v was much smaller than mc squared. It is exactly the same approximation, and also observe that this is meant to be multiplied by c squared dt squared. Okay, so it tells you if you take the square root of this, you are going to end up with instead of delta differential of t of this same quantity. This is because although Einstein was not actually using a metric, the results are equivalent to using a metric, and well, this is what we are showing here. Well, this result has to be interpreted as saying that time. Suppose that this is the tick-tack of a watch or a clock at the bottom of the box, and it clicks at intervals delta t, and these intervals are dilated by this factor into this capital delta t. This is what is observed at the top. This is the gravitational dilation of time, and this tick-tack of the clock can be related to a wave, to the frequency of a wave. So let's consider a wave whose frequency, let's delete all this. Okay, consider a wave whose frequency at the bottom is just 1 over delta t. Okay, because delta t is the period, and at the top is 1 over capital delta t. Okay, then if we take these formulae and we manipulate them a bit, you find that in terms of omega, which is just 2 pi times nu, okay, at the bottom and at the top, you can rewrite this formula in this way. So omega at the top is equal to 1 to the inverse of this factor, 1 plus, let's say, increment of phi divided by c squared. Okay, and omega at the bottom. If you again use the same approximation, you can rewrite this as 1 minus delta phi over c squared omega bottom, and then you obtain by multiplying and taking omega b to this side, you get that this is delta phi over c squared omega b, and you divide both sides by omega b, and this is the formula that typically you use. Okay, and it tells you that if you emit light with a frequency omega b at the bottom, then it will arrive with frequency omega t. Okay, and the quotient by this normalized by the frequency at the bottom is given to you by minus the increment in the potential energy divided by c squared. This is an effect which is too weak to be observed in the sun, even though the photons that come from the sun have climbed a potential which is quite large, but c squared is very, very large. However, this effect has been confirmed experimentally by experiments on Earth, and you have in the recommended references articles describing these experiments in which this is proved. This is something that does not depend on the particular theory of gravity that one uses. It only makes use of the principle of equivalence. Suppose, just to close the circle and relate this to what we know, how can I derive this from this metric that we said that describes the same situation of a constant gravitational field? Okay, that we said just a moment ago that we made this approximation, okay, mc squared, that this kind of metric replaced in the action of a particle of mass m is related to the action of a non-relativistic particle moving in the background of a potential v. Okay, we also, when we discussed this relation, we said that a better metric, which is really a metric of not just an approximation, something heuristic, a metric that can describe an accelerated system or a constant gravitational field, is the Rydler metric. And if the field is directed in the direction g, it was given by this expression minus dx squared and dy squared and dc squared, which we just ignore. Okay, so what happens at x equals 0, which remember was the bottom of the box? Well, you see that this term here vanishes, and you have the ds, that let's call it d tau, because here it is more adequate, is just dt. Okay, and I am forgetting here always this c squared. And remember, this tau has dimensions of length. At the top of there is a factor of c squared here minus the x squared and other coordinates that we don't care about. Now at x equals 0, so this is the bottom of the box, this term vanishes, and we have that ds is equal to c dt. Okay, in terms of proper time, if we want to give it also dimensions of time, this is telling us that d tau is equal to dt. Now at the top of the box, what we have is that x is equal to h, and we have ds is equal to, or if you want, d tau is equal to 1 plus gh divided by c squared to the power 1/2 dt. And this is, as we had, sorry, there is a c here, these two c's cancel, and this is the same kind of expression that we had been dealing with. Here, in these previous arguments, we always made approximations, but this is an exact relation in the context of general relativity. It satisfies all principles. We don't need much more than knowing that we got this metric from the Minkowski metric by a change of coordinates to an accelerated system. So one metric was a good metric, the other one is a good metric, and this is an exact result. Now when you make approximations, then you recover these approximated results that we wrote above. We can conclude this section by reviewing the experimental status of the equivalence principle. There are 6 main predictions that the Einsteinian equivalence principle makes. The first prediction is that bodies of any composition fall in the same way in a gravitational field, or they couple to the gravitational field in the same way. Bodies of different compositions have different kinds of atoms and nuclei, and this means that the binding energies that keep these nuclei and these atoms together, electromagnetic, weak, and strong nuclear interactions, appear in different proportions. The fact that all of them fall in the same way means that all these kinds of energies fall in the gravitational space-times in the same way, or they couple to the gravitational field in the same way. We have already seen that no difference has been detected yet, and what are the experimental bounds on the possible differences when we studied the weak equivalence principle. So let's go to the next prediction. The next prediction is that the fundamental constants of nature have to be constant in space and time. Again, no differences, no variations have been of the fundamental constants have ever been detected, and there are also strong constraints on these possible variations. You can check in the references mentioned in the program of the course what are the current bounds for these possible variations of constants, such as the charge of the electron, the Planck constant, and so on. The third prediction, which is basically that the special relativity is true locally, means is that all the experiments that you make will be independent on the particular Lorentz frame that you choose, a particular local Lorentz frame. So if you use a Lorentz frame which moves at one speed or another, you should get the same result. But also if you choose Lorentz frames with those different space-time orientations, or if in the same way, if you perform your experiment in a certain direction in space, you should get the same results if you perform it in different orientation in space. There are several experiments that have been performed trying to measure the possible differences, for instance, in the speed of propagation of light in different directions in space. No differences have ever been detected, and there are bounds for these possible differences that you can also see in the lecture notes or in the references. Time dilation, which is the effect that the astronauts in the movie Interstellar suffer in this planet, which is close to the black hole. So I recommend you that you watch this movie several times during this course to see that you understand more and more things. Is usually tested via gravitational redshift, which is related to time dilation. Gravitational redshift was measured originally by several experiments, the so-called Pound-Rebka-Snyder experiments, which used a tower of just 22.6 meters in the surface of Earth, and they measured the redshift in gamma rays sent from the basis to the top. Okay, they measured this effect with a precision of 1 part in 10 to the minus 2. Later on, the Gravity Probe A experiment of NASA was able to compare the rhythm of 2 clocks, maser clocks, one of them moving in a rocket and the other staying on Earth. And this effect was measured to a precision of 2 times 10 to the minus 4. Nowadays, this effect can be measured in tabletop experiments. Really, differences of just 1 centimeter can be detected using what are called optical lattice clocks. There is a reference in the program which is from this very year, in which you can see how there is an extensive there are extensive references to the literature where you can see other experiments, and in particular how people have been able to measure this with these clocks, which have a precision of 10 to the minus 18. Okay, finally, the gravitational bending of light was first observed in the solar eclipse, total solar eclipse of 1919. There is some discussion about whether this was really observed or the errors were too big to be for the experiment to be conclusive. The problem with the gravitational bending of light for light rays that graze the sun, the surface of the sun. So if this is the sun, you can only measure some bending for those light rays that really almost touch the sun. But the sun is not really a ball like this. It has an atmosphere, and the effect of this atmosphere is unclear. Okay, so there is, if this is the Earth, there is some uncertainty in these results, and it is not clear that it was really conclusively proven in 1919. But of course, nowadays this gravitational bending of light is seen every day with telescopes or radio telescopes, and you have this effect which is called gravitational lensing, in which galaxies or very massive bodies of mass of a galaxy deviate the light of objects which are behind in our line of sight, and these objects act as lenses, okay, bending all the light rays, so collectively they behave like lenses. Okay, so the status, you can say that it is really very healthy, and that this principle is, for the moment, there has found no contradiction whatsoever with any experiment.